So that's the way, that's the two ways people go about it in this literature. They either go after these smaller group time, they either go after the average treatment on the treated directly and then add them together to get to these interesting parameters, or they'll estimate individual level counterfactuals. That would be like a firm level counterfactual, and then they'll aggregate to the average treatment on the treated parameters that you care about. I mean, there's not a. I mean, it's just different. It's a different approach. It's a different approach to get to that average treated on the treated. All right, but ultimately, all methods are imputational. That's some are more obviously imputational, but anytime you're estimating a causal effect, it's assuming that you've identified a counterfactual. It's assuming that you've identified a counterfactual because causal effects are always based on counterfactuals. All right. So I call what we're about to do now more of like a explicit imputation, because it's going to be imputing counterfactual observations at the unit level, as opposed to this implicit imputation, which is the manual aggregation, which tends to go after. Oh, good. Okay, great. I'm glad that helped, OLS. Which tends to go after the ATT measure directly. And there's three of them, and I think I might skip. I might skip. Let's just see. I might cover John Gardner's. John Gardner's is sort of nested within this Borusyak paper by Xavier and Jan as co-authors. And then I think I will cover matrix completion because I have a paper that I think it will be forthcoming that uses it, and so I wouldn't mind promoting the method. So a little background. The very first paper in the Renaissance of diff and diffs, if you want to kind of call it a discrete change in the diff and diff literature, is the Krill, Borusyak, and Xavier's Jaravel paper from 2017. And let's just look at it real quick. This paper was the very first one. Let's go to Scholar. Actually, let's do it over here. Scholar. Revisiting event studies. It's already been cited 427 times. I think it came out in 2017. I think this is an update. Right here. But this was the very first paper on diff and diff. This was of the new diff and diff papers. This was the first one. Krill is now at University College London, and Xavier is at, I believe, LSE. But I don't actually know if Xavier was a graduate student. The latest version is here. Yeah, just curious. He took it down. Yep, they took it down. So that paper, Krill and Xavier really focused on other work. They focused on other work, like their Krill has this paper in Restud on the Bardic instrument. That ended up getting a lot of their attention, and they circled back to this paper 4 years later or 3 years later when they added Jan. And that paper is the one I'm going to discuss. This is a successor. So my interpretation of the paper is that it's a damning critique of OLS two-way fixed effects. We've kind of already discussed a lot of this material, so I might go over some parts of it relatively quickly and then get into the explicit imputation, because a lot of the critiques of two-way fixed effects we already know. Some stuff we don't know, though. So I want to cover some things. Some of the stuff we learned from Andrew Goodman Bacon. Some of it we learned from Sun and Abraham. So here's my outline of their paper. This is not their outline. This is how I have understood their paper. They're going to discuss their interpretation of... I'm going to discuss their interpretation of the basic diff and diff assumptions. I'm going to discuss their critique of two-way fixed effects when the strong assumptions don't hold. I'm going to discuss their new assumptions, and then I'm going to look at their robust, efficient imputation estimator. That's it. All right. So under three standard diff and diff assumptions, two-way fixed effects, OLS will be fine. And not surprisingly, they're going to include no anticipation, parallel trends, treatment effect, homogeneity. Right? So it's like that's like the thing you need for OLS to perform well is treatment effect, homogeneity. And it's got to do with the way in which OLS does extrapolation. And when you have treatment effect homogeneity, you really can extrapolate beyond, like, you can extrapolate forward in ways that won't matter because you will have estimated a treatment effect. So then when you extrapolate, you can still use that information. When there's treatment effect heterogeneity, you can't do that. Theirs was the first one to bring this up. After they do their detailed critique of two-way fixed effects, they're going to introduce this robust estimator. And since it's OLS based, it's blue. It's the most efficient of the linear unbiased estimators. So a key flavor, this kind of gets at OLS question about manual aggregation. The estimation targets are usually an average treatment on the treated, but it will be it'll be a weighted average of individual level treatment effects. So they're going to get individual level treatment effects and they're going to weight them. All right. But the problem is weights don't have to add up. Oh, sorry. No. You don't have to have the weights add up to 1. All right. We have a number of options, but this is kind of like what we're after. We're after tau. I'm using their notation. I usually say delta, but they use tau. So let's talk about the assumptions, parallel trends. Okay, real quick. This is their assumption. They're saying in a world where there's no treatment, then the outcome is determined by a unit level fixed effect. Time dummies, error term. That's explicitly what is done here. Right there. In that specific thing right here. Because notice, this is talking about Y0. That Y0 is in a world without treatment. So that would mean that this is gone. Right? And in a world without treatment, outcomes will just be based on firm fixed effects, time, or you could put in time fixed effects, and an error term. Well, that's what this is. Okay? So this is a two-way, I gotta fix that. This is a two-way fixed effects model of the parallel trends, right? And you've got this error term equaling 0. Well, look, error term equaling 0. Look at that, on average equal to 0, right? So that's explicitly what we've been working with the Baker data. No anticipation. We've been talking about that one too. So what that means is absent prior to the treatment, there is no treatment effect. That with Orley Ashenfelter's dip, and it is where you know that you're about to be unemployed and you're about to sign up for this job trainings program, and you might start spending now. Imagine a grad student, a PhD student gets a job in March and then starts in the fall. They might go ahead and start making purchases now to get ready for the fall and then just pay it back when they get their first paycheck. And that kind of like consumption smoothing type of behavior is being ruled out. So what that basically means, though, in a way, is just that you have to be careful about when you define the start date of the treatment. Maybe the start date of the treatment isn't August of the year, it's March. The day you got the job, not the day you started, right? So Ashenfelter's dip is usually describing these situations pre-treatment where there is anticipation. And so we're looking at that period of time where there is no anticipation, which would be the period just prior to Ashenfelter's dip occurring. It's an extension of Sattva because Sattva requires that your outcome be a function of your current treatment status and not your future treatment status. As an assumption, it literally imposes that tau equals 0 for all treatment periods. This is why this is a great paper to follow up from Son and Abraham. That all diff and diffs require some form of this assumption. Otherwise, you don't have a reference group. So you need this because you need to have a baseline. So it's kind of like implicit in all of your diff and diff calculations that you need no anticipation. But like I've seen so many diff and diff papers presented, and they'll say they just need parallel trends. They won't say that they need no anticipation, but you need it. So it's oftentimes treated as like an implicit assumption that can be tested using an event study. But that's going to actually confuse estimation and identification. And then they discuss these restricted causal effects. This comes up a lot. I'm just kind of remember how my pedagogy is to teach the paper. So this is something that comes up in their paper, Assumption 3. They're going to say, we're going to place restrictions on what treatment effects can and can't be. This is this set of authors is so specific with how they express assumptions. Another econometrics team like that is DeChase Martin and Hopeful. They're very much like that. Pedro's like that. But here they don't even say treatment effect homogeneity. They just say restricted causal effects. You're only going to allow the causal effects to be certain things. So if we can assume something like homogeneous treatment effects, then actually two-way fixed effects is the best thing you can use because it can correctly extrapolate and won't, have any effect on inference. But when A3 is not tenable or not really ex-ante justified by theory, then we should be worried. And they're going to have this A3 prime that is a slight modification. But if you think that you have homogeneous treatment effects, you should use two-way fixed effects. The problem is having a theory that says treatment effects should be homogeneous. And just because you have a theory, I don't know if that means you should use it because your theory could be wrong. My thoughts. Those are my opinions. So they're going to critique common practice. Common practice is just to run event studies with two-way fixed effects under differential timing, right? Every event study before 2020. Not everyone, most of them, right? So you're going to get three things when you do this. You're going to get under identification in the event studies. We kind of discussed this with Son and Abraham, right? So we'll talk about it again. You're going to get negative weights, which we saw a little bit of that with Son and Abraham, but this is actually even in the static. You're going to get, actually I'm not sure if it's in the static, but you can get negative weights. And the problem with negative weights is that you can when you have negative weights, you actually can't interpret as easily the average, the final coefficient as like a weighted average over all treatment effects. Sorry. And then you can get spurious long-run causal effects. So the under-identification problem, we saw some of this with Son and Abraham, but remember there were these simultaneous discoveries. Simultaneous discoveries happen. There was a simultaneous discovery of two-stage least squares back in the 50s by two different writers. Even the signaling model. Michael Spence discovers the signaling model, and the philosopher David Lewis discover the signaling model at the exact same time. Pretty much 1 year apart. I wrote Michael Spence and asked him, did you ever hear of David Lewis? He didn't hear him. I mean, he's a philosopher, but in his dissertation, he has a signaling model. They both were influenced by Schelling. So it's like this, but Schelling's not doing signaling models either. So it's kind of wild. So all of this work has simultaneity issues too. So the result about this under-identification problem was in Borusyak and Xavier's paper, as well as Son and Abraham. But basically what it means is if you don't have any never treated units, then you can't estimate those pre-treatment leads. They say it's because you could fit a line through them, and what they're basically saying is that in relative time, in relative event time, it's got this second multicollinearity problem, and so you can't distinguish it from just a linear trend. So this is why Borusyak and Xavier, Kirill and Xavier say you're going to have a multicollinearity problem with differential timing, so you need to drop two periods, not just one. Okay. So they say the under identification of lead coefficients. That was when, just to show you where this was. Here. This is what Son and Abraham meant by the same thing. Okay. Multicollinearity. So I'll just read it. Formally, the problem arises under identification. Formally, the problem arises because a linear time trend T and a linear term in the cohort E can perfectly reproduce a linear term in relative time. Basically, they're describing a multicollinearity problem. They've got this perfect multicollinearity in relative event time. Therefore, a complete set of treatment leads and lags, which is equivalent to the fixed effect of relative time, is collinear with the unit and period fixed effects. So you can't do it. So you have to have an additional normalization. All right. You need to drop another unit. That'll break another lead, and that'll break the multicollinearity. Problem is, you need to have, they make a really good point. You need to have a reason for which one of these you're dropping. So it matters which ones you drop, because in that population regression coefficient on the lead, those ones you drop still kind of end up contaminating the effect. So this is about no anticipation. If you choose, to drop leads -4 and -1, then you had some theoretical reason to assume that no anticipation held for them and not some other periods. So researchers need an a priori reason to justify which leads they drop. I had a great one in my paper. Craigslist they didn't announce or advertise or communicate that they were going to enter a market before they did. So no anticipation was guaranteed. That might not be enough for the lead to be uncontaminated, because remember, the lead is going to be contaminated by cohort average treated on the treated from other periods, and under treatment effect heterogeneity, they don't negate. So, but you need to kind of scrutinize this. Secondly, so I said this here, negative weighting. So this is the second thing that's problematic with two-way fixed effects under differential timing. You end up with these negative weights. When you have heterogeneity, the first paper as well as the second paper showed there was a problem for traditional event studies. We saw this earlier with Son and Abraham. What happens is that with heterogeneity, the weights on the treatment effects can become negative. So assume some simple static model, but this is not just with the event study. This is even with the static model. Assume some single dummy for treatment. They have this second lemma. If assumption 1, parallel trends, and assumption 2, no anticipation, hold, then the estimand of the static OLS specification is this weighted average of all those individual level treatment effects for some weights. And they add up to 1. So the static OLS estimand cannot be interpreted as a proper weighted average because some of the weights can be negative. And that's like a really common thing in this literature, is to be very worried about negative weighting, because the negative weighting can basically cause a coefficient to no longer even be the right sign. So there they give an example of it. They've got 3 event dates. Yeah. So these are like, 1986, 92, and 98. And you've got you have two dates, E, and you have 3 years. Sorry, that's 3 years, T1, 2, and 3. Okay, and so in each year you've got some particular value. All right, and group A is going to be treated in the second period, and group B is going to be treated in the third. Right, and you're wanting to estimate delta from a static parameter. And what's delta? Here, differential timing. You're estimating it with differential timing delta. Okay, this is what you get from the static representation. You get the delta A2, you get the delta A3, you get the beta 3. All right, so you get all three of these, but they're weighted in a weird way. All right, so the weights sum to 1. All right, see this? So the weights are summing to 1. 1/2, negative 1/2, that's 0, weight of 1. All right, which is what we said over here. They sum to 1. But some of the weights can be negative, like this one. And what that means is you're going to get this negative weighting on it's going to have this attenuation bias. In a way, this is like what Andrew Goodman-Bacon found. That's what Andrew Goodman-Bacon found. Although here it's just saying that it doesn't. I don't think it's as clearly related to heterogeneity. It's not as clear. Although if it is heterogeneous, if it is homogeneous, that cancels out and you'll end up with just this 1. But if it's heterogeneous, then you've got this, final term here lagging it down. So notice when you don't have homogeneity, you have this attenuation bias on the static parameter. So two-way fixed effects has this severe short-run bias. The long-run effects, which is what this is right here. Oh, sorry, right here. This is the long-run effect. It's getting further out. It's getting more negative, or downwardly, biased towards 0. So the long-run causal effect corresponding to the early treated unit A in the late period 3 enters with a negative weight. So the larger the effects in the long run, the smaller the coefficient will be. And it's caused by what Borusyak, what Krill and Xavier call, and Yan call, the forbidden comparisons, those late to early treated contrasts. We saw this with Goodman-Bacon. So forbidden comparisons create this downward bias on long run effects with treatment effect heterogeneity, but not with treatment effect homogeneity. So it really is a homogeneity violation. Because if you had homogeneity, like I said, that would cancel out. You'd be left with just that, which you would think, well, but we're losing A3 and we're losing B3. But remember, they're all the same. Under treatment effect homogeneity, that is equal to that is equal to that. So it doesn't really matter. So you identify one of them, you've identified all of them. And then the last, remember here what they're doing, spurious long-run causal effects. So with that heterogeneity, this time long-run effects where there are none is real common. So basically you need to impose a lot of pre-trend restrictions to get estimates of long-run coefficients. Even then you can't get them all. So OLS estimates are fully driven by unwarranted extrapolations of treatment effects across observations and may not be trusted unless you've got really strong reasons to believe in homogeneity. So let's say you don't have any never treated units and you let H equal the max number of event states minus the min number of event states. There are then for any non-negative weights, any positive weights, the weighted sum of causal effects is not identified. So you can't even get the coefficient. So what do? They're going to modify that parallel trends assumption, and they're going to change that slightly, and they're going to now have this assumption for homoscedastic residuals. And the reason they're doing this is because now they're introducing this efficiency property with their estimator. So now we're going to have 4 assumptions, A1 prime to A4, and I believe they're going to drop A3. So I think it's A1 prime, A2, and A4. So we're going to lose the homogeneity assumption, and we're going to get the efficient estimator, which is for all linear unbiased estimates of that weighted delta, that efficient estimator can be obtained with 3 estimates in it, 3 steps, and it's efficient. So what are we doing? This is the weird part of this paper. All right, they're going to impute counterfactuals for every single firm, and then they're going to aggregate to delta W. So they're going to use OLS to estimate counterfactuals, and then once they have counterfactuals, they're going to aggregate up to delta. But it's how they do it. So this is how they do it. Here's a quote I found though or I think I got the quote from them. At some level, all methods for causal inference can be viewed as imputation methods, although some more explicitly than others. And the idea is to estimate Y0, okay, using the untreated observations and extrapolate it to impute the counterfactuals for the treated. So what they're going to do is they're going to run a regression on Y0, all right? They're going to get coefficients on all of those parameters. All the fixed effects parameters, they're going to get coefficients. They're then going to impute counterfactuals for their treatment group using those estimated coefficients. They're going to show that it's consistent. So they're going to estimate expected potential outcomes using OLS on the untreated observations. And then they're going to calculate delta hat at the individual firm level or individual level as the observed outcome minus the fitted value. This is a lot like synthetic control in a way, because you're estimating the missing counterfactual. You're estimating the missing counterfactual at the firm level. Once you get that, you're going to then estimate target parameters as weighted sums. So the only thing that's really making this different than those manual aggregations is that they're not aggregating average treatment effects. They're aggregating individual level treatment effects. It's an explicit imputation. There will be a column of data representing y hat 0. All right, so you'll get a larger data set before you do any of the aggregation. That's not what you get with Callaway and Santana or Son and Abraham or to Chase Martin and DeHolfel. So think back to that original statement of the parallel trend assumption. You're modeling Y0. Without treatment, potential outcomes don't depend on any treatment effect. So we don't have to worry about treatment effect heterogeneity because when we are just working with this here and we have treatment effect heterogeneity, but we're just running our regression based off the untreated units, then it's fine because it's going to follow that, it doesn't depend on treatment effect heterogeneity, all right? It doesn't depend on it. So we're then going to use, if we had done this here, then we would get coefficients on firms, coefficient on year dummies. There wouldn't be a coefficient here, but we would get it here, and we would estimate Y0 for all the untreated units, but also for the treated units. Okay? So, like you could run this. All right? And then you would say like, predict y hat if treat equal 0. Oh shoot, no, I'd go xt reg y I dot firms I dot n. Do it that way. Do it n. No, do it I dot n. Actually, it goes I dot n fe I. Man, I haven't done this in so long. Robust. I think that's how it works. Yeah, ts set id here. xt reg y I dot n fe I id robust. Okay. Oh, I didn't do it right. Okay, so I got to do this. I got to run the regression on the TE 0 group. Do that. Oh, I don't have any. I got to do it for the never treated. I got to do it for the not yet treated. I thought I had TE. Oh, treat. Sorry. I was about to say. Okay, so I get this regression I've run on 15,000 observations because I have 15,000 untreated units. And then I'm going to say predict y hat. Now look at y hat. 30,000. Well, what happened? I imputed counterfactuals for everybody using the coefficients on the year dummies and the firm fixed effects dummies. I did it for everybody. So you have here, without treatment, oh, sorry, let me, yeah, we're good. All right. So we're going to obtain consistent estimates of the fixed effects, which under parallel trends will be consistent estimates if we assume this right here, this two-way fixed effects model. We can get the consistent estimates of the fixed effects, and then we can use that basically to model the missing counterfactuals for each unit because they all follow the same trend. Okay? I don't know. I guess I don't know, is it a cool trick? I think I didn't think to do that. Gardner thought to do that, but I didn't. But it's very computationally fast, it's efficient, and it's very flexible to things like unit trends, triple diff, covariates, and so forth. But remember what we said about covariates. So, but still, nevertheless, you can do it. So you are going to perform your pre-trend test on the untreated sample only. They say that this is better because it presents the conflation of using an identification assumption and validating it. So traditional regression-based tests use the full sample, and they recommend using that includes the treated observations. They recommend using just the untreated units. Therefore, it's not a test for A1 and A2. It's anyway. So choose an alternative model. Estimate delta with delta hat using OLS on untreated units only. Test that delta equals 0 using an F-tester visually. All right, that's what you're doing. And then you've got this performance of the estimator. You've got this performance of the estimator. And they compare their estimator to DeChase Martin and Son and Abraham. And they're just looking at the efficiency and the bias of alternative estimators. So basically what you see here is that the variance typically is lower. The variance is lower. We put in more periods, it's lower. You have heteroscedastic residuals, so you lose that assumption 4. The estimator still has lower variance. If you put in various kinds of weird AR1 residuals, it still usually is better. And if you put in anticipation effects, it's still better. Usually, not always. Down here for these longer leads, longer lags, it's not as much. Okay, so let's take our break and come back in 5 minutes on the hour. 5 minutes on the hour. Okay. All right, we'll come right back.